In this video, I am going to talk about the multi-computer system. And the network traffic is much lower than multiprocessor system, CPU to CPU versus CPU to memory. Bus-based multi-computer. We can see the bus-based multi-computer. It looks topologically similar to the bus-based multiprocessor, but since there will be much less traffic over it, it need not be a high-speed backplane bus. In fact, it can be a much lower speed learn, typically at 10 to 100 Mbps compared to 300 Mbps and up for a backplane bus. The, the upcoming diagram in the next slide, it's showing more often a collection of workstations on a LAN than a collection of CPU cards inserted into a fast bus. As switch-based multi-computers, this category consists of switched multi-computer. Various interconnection networks have been proposed and built, but all have the property that each CPU has direct and exclusive access to its own private memory. This diagram, it shows two popular topology, a grid and a hypercube. Grids are easy to understand and layout on a printed circuit boards. They are best suited to problems that have an inherent two-dimensional nature, such as graph theory or vision. A hypercube is an n-dimensional cube. The hypercube is shown in the diagram. Right-hand side B diagram is four-dimensional. It can be thought of as a two ordinary cubes, each with 8 vertices and 12 edges. Each vertex is a CPU. Each edge is a connection between two central processing units. The corresponding vertices in each of the two cubes are connected. The software concept. Loosely coupled software allows machines and users of a distributed system to be fundamentally independent of one another, but still to interact to a limited degree where that is necessary. Consider a group of personal computers, each of which has its own CPU, its own memory, its own hard disk, and its own operating system, but which share some resources such as laser printers and databases over a LAN. This system is loosely coupled since the individual machines are clearly distinguishable, each with its own job to do. If the network should go down for some reason, the individual machine can still continue to run to a considerable degree, although some functionality may be lost. The network operating systems. A typical example is a network of workstations connected by a LAN. In this model, each user has a workstation for his exclusive use. It may or may not have a hard disk. It definitely has its own operating system. All commands are normally run locally right on the workstation. However, it is sometimes possible for a user to log into another workstation remotely by using commands such or login machine. The effect of this command is to turn the user's own workstation into a remote terminal logged into the remote machine. Commands typed on the keyboard are sent to the remote machine and output from the remote machine is displayed on the screen. To switch to a different remote machine, it is necessary first to log out, then to use the R login command to connect to another machine. At any instant, only one machine can be used and the selection of the machine is entirely manual. The example of a network operating system with two clients and a server is shown in this diagram. One approach is to provide a shared global file system accessible from all the workstations. The file system is supported by one or more machines called file server. The file servers accept requests from user programs running on the other machines called clients to read and write files. Each incoming request is examined and executed and the reply is sent back. That is shown in this diagram. In this diagram, different clients may mount the servers in different places. File servers generally maintain hierarchical file system, each with a root directory containing subdirectories and files. Workstations can import or mount these file systems, augmenting their local file system with those located on the servers. For example, as shown in this diagram, two file servers are shown. One has a directory called game, while the other has a directory called work. These directories each contain several files. Both of the clients shown have mounted both of the servers, but they have mounted them in different places in their respective file system. Client 1 has mounted them in its root directory and can access them as a /games and /work respectively. Client 2, like client 1, has mounted games in its root directory, but regarding the reading of mail and a news as a kind of game, has created a directory called /games/work and mounted work there. Consequently, it can access news using the path /games/work/news rather than /work/news. While it does not matter where a client mounts the server in its directory hierarchy, it is important to notice that different clients can have a different view of the file system. The name of the file depends on where it is being accessed from and how the machine has set up its file system, because each workstation operates relatively independently of the others. There is no guarantee that all present the same directory hierarchy to their programs. The merits and demerits of networking operating system. The advantages of network operating systems are centralized servers are highly stable, security is server managed, upgrades to new technologies, remote access to server is possible. The disadvantages of network operating systems are high cost of buying and running a server, dependency on a central location for most operations, regular maintenance and updates are required. True distributed systems, tightly coupled software on loosely coupled hardware. The goal is to give an illusion as single time sharing system called single system image or virtual uniprocessor. The characteristics of a true distributed system is a single global interprocessor communication mechanism. Global protection scheme is also available. So process management must be the same. A file system also must be the same. Multiprocessor time sharing system is a tightly coupled software on tightly coupled hardware. Example, multiprocessor that are operated as Unix time sharing system, 32 to 30 million instruction per second CPU, then 960 MAPS CPU. Important characteristics are existence of a single run queue, a list of all the processes in the system that are logically unblocked and ready to run. Organization of the system differ from the network operating system and true distributed system. A multiprocessor with a single run queue. The important characteristics of this class of system is the existence of a single run queue, a list of all the processes in the system that are logically unblocked and ready to run. The run queue is a data structure kept in the shared memory. As an example, we can consider the system which is shown in the figure and displayed on the screen, which has 3 central processing units and 5 processes that are ready to run. All 5 processes are located in the shared memory and 3 of them are currently executing. Process A on CPU 1, process B on CPU 2, and process C on CPU 3. The other 2 processes, D and E, are also in memory, waiting their turn. The comparison of 3 different ways of organizing n number of central processing units. It is shown on this diagram. It is showing the differences between the 3 kinds of system we have examined so far. Probably the single most important issue is how to achieve the single system image. In other words, how do the system designers make an illusion effect to everyone into thinking that the collection of machines is simply an old-fashioned time-sharing system. A system that realizes this goal is often said to be a transparent. With respect to software concept, distributed operating system and networking operating system. Distributed operating system, tightly coupled operating system for multiprocessors and homogeneous multicomputers. Network operating system, loosely coupled operating system for heterogeneous multicomputer, LAN and WAN. Middleware, additional layer, a top of network operating system, implementing general purpose services. Decision issues, we can list out the decision issues. The first one is the transparency, flexibility, reliability, performance, and scalability. Transparency should be achieved as a single entity by the users. Users should be unaware of where the services are located, and transferring them to a local machine to a remote one should be transparent. Achieved in an easy way to hide the distribution from user. Example, Unix make command. Hiding is harder, but also possible through the system call interface by issuing them call to read files. Transparency, the concept of transparency can be applied to several aspects of a distributed system. The first one, location transparency. The users cannot tell where resources are located. Second type of transparency is migration transparency. Resources can free to move without changing their names. Then replication transparency. The users cannot tell how many copies exist. The fourth one, concurrency transparency. Multiple users can share resources automatically. Then parallelism transparency. Activities can happen in parallel without. So in this diagram, monolithic kernel and microkernel has been shown in this diagram. The monolithic kernel is basically today's centralized operating system augmented with networking facilities and the integration of remote services. Most system calls are made by trapping to the kernel, having the work performed there, and having the kernel return the desired result to the user process. With this approach, most machines have disk and manage their own local file system. Many distributed systems that are extensions or limitations of Unix use this approach because Unix itself has a large monolithic kernel. If the monolithic kernel is the uh, champion, the microkernel is the up and coming challenger. Most distributed systems that have been designed from scratch use this method. The microkernel is more flexible because it does almost nothing. It basically provides just four minimal services. Number one, an inter-process communication mechanism, some memory management, a small amount of low-level process management and scheduling. And then fourth one is low-level input and output. So in this screen, micro versus monolithic kernel comparison is given in terms of size, in terms of execution, extendable, whether it is easily extendable or very hard to extend, and security point of view, then core and then examples also have been given in this table. Next one is reliability. The goals of building a distributed system to make them more reliable than single process system. The idea is that if a machine goes down, some other machine takes over the job. It has three important aspects. One is availability, second security, and third one is the fault tolerance. Availability means a highly reliable system must be highly available, but that is not enough. So data entrusted to the system must not be lost and garbled in any way, and if files are stored redundantly on multiple servers, all the copies must be kept consistent. In general, the more copies that are kept, the better the availability, but the greater the chance that they will be inconsistent, especially if the updates are very frequent. Reliability is continued in the screen. Security in a distributed system, but it is very hard to achieve the security, no name or identification field in the incoming message. Second, fault tolerant. The distributed system can be designed to mask the failure to hide them from users. The performance, always the hidden data in the background is the issue of the performer. Building a transparent, flexible, reliable distributed system, more important lies in its performance. In particular, when running a particular application on a distributed system, it should not be appreciably worse than running the same application on a single processor. Performance metrics used. The first one, throughput, response time, system utilization, amount of network capacity consumed. Performance problem is often due to communication. So solution to reduce the number of messages communicated as far as possible. Performance and the parallelism based on the grain size of all computation, fine-grained or coarse-grained computations. Fine-grained means jobs involving large number of small computations, high interaction rates, and more data. Then coarse-grained jobs involving large computation, less interaction rate, and little data. Scalability, centralized services, a single server for all the users. Centralized data means a single online telephone book, centralized algorithm doing routing based on complete informations. Centralized services, many services are centralized in the sense that they are implemented by means of only a single server running on a specific machine in a distributed system. Problem with this scheme is very obvious. The server can become a bottleneck as the number of users and application grows. Even if we have a virtually unlimited processing and storage capacity, communication with that server will eventually prohibit the further growth. Centralized data, having a single database would undoubtedly saturate all the communication lines into and out of it. Domain name system. DNS maintains information on millions of computers worldwide and forms an essential service for locating the web server. If each request to resolve a URL has to be forwarded to that one and only DNS server, no one would be using the web. Centralized algorithm, enormous number of messages have to be routed over many lines. Optimal way to do this, collect complete information about the load on all the machines and lines, run an algorithm to compute all the optimal route, spread this information around the system to improve the routing. These messages would overload the part of the work. The solution for this to use the decentralized algorithms. Characteristics of decentralized algorithm. No machine has complete information about the system state. Machines make decisions based only on local information. Failure of one machine does not ruin the algorithm. There is no implicit assumption that a global clock exists. Scaling techniques, hiding communication latency, distribution, and the replication.